Okay, welcome, welcome. Okay, so close this. You just can't really see me that well. Is that better? Is there like a nice middle? My camera auto focuses, so it's like either my face is really bright or my face is really dark. And that's really dark. So that's half and half. Okay, whatever. I'm gonna close it the whole way so my face is bright. Okay, welcome. I hope you had a good weekend. Now, I did grade exam 2, or exam 2. I inputted the grades for exam 2. And I had to modify exam 1 grades. And let me explain why I did this. Okay, before you all run out and go grab your pitchforks. And, you know, I get some sort of angry mob on my hands. Okay, teaching online is different than teaching in the classroom. Okay. The online modality is a little different, okay? And I never gave my first exam in an online format. And so generally, students don't do that well on the first exam, okay? And I have to be a little bit more generous in the way that I grade the first exam, and I have to curb those grades. However, it turns out that that's not the case for this class. And so instead of being too generous in the beginning and giving people a false sense of security, I wanted to be more generous towards the end, aka towards the final, and that gives me more control over the overall outcome of each individual grade. I teach statistics as well, so I can modify the grades any way I want to. Okay, that's just the power of statistics and the power of grading and the power of a sample size of about 32 students. Okay, when you learn how to teach statistics, you can modify the statistics any way you want. Let me show you the breakdown of basically where the class is at right now. Okay, and why I had to go back and modify the curving that I did at the beginning. Okay, that doesn't mean that the grades aren't going to be curved toward the end. They will be. Okay, I just wanted to basically mirror what's in WebAssign right now in Canvas, so that people don't get a false sense, like I said, a false sense of security. You know, they're not setting them up for failure. That, you know, they're like, oh, well, I have a 75% in the class and I'm good to go and I can just continue at this low rate of performance. And then, you know, they don't do so well the next 2 exams and they don't turn in all of their homework and they're like, oh, now I'm failing the class. Okay. So, you know, because in this class is not a bell-shaped curve. Okay, and I hope you know what I mean by a bell-shaped curve. That this class is not a bell-shaped curve. This class is a logistic curve. Okay, when it comes to difficulty of material. This is a logistic curve class. Let me explain what that means real quick. Okay. Let me share my screen. Okay. So, okay, some classes have a bell-shaped curve. They go up and they come down, and maybe at the peak of the class, you know, it's really hard. Okay, maybe toward the beginning of the class, the material is not as difficult, and toward the end of the class, it may not be as difficult. We're winding things down. Okay, that is not this class. Okay, this class is not a bell-shaped curve. This class is what's called a logistic curve. Okay, this is a logistic curve or a log normal curve. And a logistic curve looks like this. Okay, where you have an asymptote. And so the level of difficulty of the material keeps going up and up and up and up and up, and we're about right here. It keeps going up and up and up and up. Okay, this would be like chapter 12, chapter 13, chapter 14. This is chapter 15 and chapter 16. Okay. So again, I don't want to scare anybody, but I also don't want people to come in with a sense of overconfidence. Okay. So the material will get increasingly more difficult. Chapter 16 is the most difficult chapter. That and some parts of chapter 12 are actually pretty difficult too, but you know, we're just dealing with vectors and stuff. This chapter 16 is a beast, and it's basically physics on steroids, and it's all the engineering applications of multivariable calculus. Okay, I'm just going to let you know that right now. Okay, so this class is a logistic curve in level of difficulty. Okay, and then you may get, again, you may get some classes where it just it stays moderate the entire class. Okay, and so you might say, oh, well, you know, it's a uniform distribution of the difficulty level, right? Okay, so now, with that said, people are doing pretty well so far in the class, which is good. Okay, so what does pretty well mean? Well, let's look at the data here, shall we? Okay, so the data that I crunched, okay, is right here. Let me share my screen. Okay, so this is the raw data from the class so far. And if you look at the raw data, okay, I have 20 people getting an A or B. I have 6 people getting between a D and a B. I have 3 people getting less than 60%. I have 1 person getting less than 40%, and I have 2 people getting less than 19%. These are people that I'm going to be dropping, by the way. So these 2, you can just kind of ignore them. Okay, but we see the distribution here. Now, you can even see the distribution a little bit better if I change the bin numbers here. So if I take the bins and I go to bin 10, right, which is your normal A, B, C, D distribution, boom, now ignore the outliers. So what is this showing? Well, it shows me that I have about 13 A's right now in the class. I have 13 A's, I have 7 B's. So that's 13 A's. That's almost half the class has an A. So that's amazing, amazingly well. So again, that is why I felt there was no need to curve the first exam. So if your grade went down, okay, you know, and you're very mad at me because your grade went down, again, in the cohort that you're in, you're being compared to all of these 13 A's and these 7 B's. If you're at 2/3 of the class has an A or a B right now in the class, with us being about halfway, at the halfway mark. We have 2 more exams and a final. So we're about 2/5 of the way through. So again, I just wanted to kind of explain why I had to adjust the grades I did. Some of you guys went down 5%. Some of you guys went down 10% on the first exam. However, I will be modifying and curving these things. Now, if I were to curve the grades based on a bell curve, this is not a bell curve. This is not a bell curve at all. The people who would be getting A's right now would be getting screwed, just to help people who would be getting lower grades. So there's no way I'm going to do a bell curve in this class. That would be completely unfair to the people who are doing really well. So I have to err on the side of 1, and that's basically, I don't want people being overconfident in the beginning, you know, so that I have to, you know, be the bearer of bad news later on. I hope that makes sense. Again, I went over and over this in my mind. I knew that I was going to piss people off. But again, I pride myself on being incredibly fair when it comes to my grading. And I would rather err on the side of caution in the beginning than err on the side of generosity and set people up for failure. Okay? I hope that makes sense. And if you have any questions or comments, please do not hesitate to let me know. Okay. Does that make sense? Is there any questions or comments about that at this point?
I have one question, Professor.
Yes.
My question is like, I'm not asking for curve but for example, for exam 1 or exam 2, you know, the WebAssign just take the final answer. And if you look for some students, some steps, maybe all the steps, 90% correct, but just the final answer is wrong. Do you see it's fair, like just to take the final answer as the final grade, or this is my question?
Yeah, that's a great question. I do at this point feel that it's fair, simply because what you're doing in your homework is you're training yourself to do that exact same thing. And you know, I will look through the exam, and there are cases where people will email me and say, hey, you know what, I screwed up on the final answer, but could you please look at my work? And if you are one of those people, then I will look into the work, and if you got the work correct in your final answer, then I will gladly award you those points for the problem. Okay, but again, I'm trying to create a level playing field at this point, and maybe I'll have to modify that at the end, but you know, I couldn't justify inflating grades right now, inflating the WebAssign grades right now. Again, the final exam is not on WebAssign, so just keep that in mind. It's a take-home exam. So the final exam is a take-home exam, so that really shows me what you know and what you don't know. But I do feel that it's, you know, I don't know. I mean, I'll have to think about it. It's a great question.
Thank you.
Yeah, you're welcome.
So for the final, are you gonna do the proctorial for that?
For the final, I mean,
this is a take home, right?
It's take home. So I think I give you 24 hours to do it and return it. But I'll talk more about that as we get closer to the final exam. Okay. Okay. So, okay, let's go over number 15, chapter 15. Let's start chapter 15 today. Okay. Okay, 15.1 and 15.2. Okay, we're going to talk about double integrals now. Oops. Okay, so double integrals, 15.1, 15.2. We're kind of on the home stretch at this point. You know, we're kind of going downhill. We've got 2 chapters left for the class. Sorry about that. Turn this off. Okay, double integrals over rectangles. Okay, 15.1. Okay, the double integral of f over the rectangle R is, okay, over a rectangular region. Okay, think of the region R as the domain, okay, over the domain on the xy plane, okay, is the integral over R of f of xy dA is equal to the limit mn, as m and n go to infinity, of the summation of I equals 1 to m, okay, k equals 1 to n, okay, of f of x star I k, okay, y star I k, delta A. Okay, so we're summing up all of the tiny little rectangles, okay, over this region, and we're creating a column with their heights. So let's say that m and n were 4 here. Okay, let's say that, okay, m equals 4 and n equals 4. Okay, so saying that, you know, we get 4 widths and 4 heights on our xy plane. Okay, then what we would get is we would get something that looks like this. Okay, we would get, we'll say these are squares. They don't have to be squares, but we'll just say that they're squares. Okay, so this is R. This is my R, and we've got 4. Okay, we've got 4 little areas there. Okay. Actually, this would be 2. My bad. M would be 2 and N would be 2. Okay. So it's 2 by 2, 2 by 2 squared. Okay, and so if we had a surface, okay, if we had a surface over this, okay, over this region, okay, what would this look like? Well, it would be these columns. Okay. We'd get these columns here on the surface, okay, and it would be an approximation of the volume under this surface. Okay, so we're saying that this is f of xy. Okay, so we want, for a double integral, just like we wanted the area under a curve, this is, the double integral is a volume under a surface. Okay, so think of that analogy. Okay, this is a volume on the surface. So we're using this Riemann sum as an approximation, okay, as an approximation for the volume under the surface. What am I doing wrong here? There we go. Okay. Does that make sense? So we would end up with four, right? We'd end up with these points, okay, that are actually on the surface. We have those points that are on the surface, and then we have these four columns, these four buildings, four blocks. Okay, they're actually called rectangular prisms. So we'd have these four rectangular prisms that would now be an approximation of the volume. This is an approximation of the volume under the surface inside R, okay, inside that rectangular domain of R. Okay. Okay, so let's do this. Let's take example 1 here. Estimate the volume of the solid that lies above the square R equals 0,2 by 0,2, okay, and below the elliptic paraboloid z equals 16 minus x squared minus 2y squared. Okay, 16 minus x squared minus 2y squared. Okay, so we want to estimate the volume. Okay, and so what I'm going to do here is something called a right-hand estimate. Okay, we have four corners that we can estimate with. I'm going to do a right-hand estimate. Okay. Okay, and I'm going to say that the points closest to my right hand in front of the paper. Okay, so it's the front right. I'm going to take the front right points, the points that are closest to me on the right. Okay, points closest to my right hand in front of the paper. Okay, does that make sense? So, okay, let's get a real diagram for this so that I don't completely mess it up. So let's go to let me share my screen here. Now the book has a really good diagram of this, and I just want to make sure that you understand which points we're looking at before I totally mess up the drawing. Okay, so let me go here and let's go to documents. Let's go to Santa Ana. Let's go to Math 280. Let's go to PowerPoint. Let's go to Stewart. And let's go to 15.1. And let's see what happens when we do this. And let's go to the right slide. There we go. Okay, so here's the right slide for this problem, okay? And so what points are we going to use? Well, we're going to use this point here, this point here, this point here, and this point here. Does that make sense? It's the one that's closest to me as the viewer, but on the right side. Okay, and those points on that surface, this elliptic paraboloid, those points on that surface, maybe I should have used a different color. Okay, I don't know if they're going to allow me to use a different color, but I'll just make them bigger. Here we go. There's a big point, there's a big point, there's a big point, and there's a big point. Okay. And so these points are the points that are going to give me the height or my z value, okay, at these values, okay? Well, where are these values located? Well, where are these points located? Well, these points are located at 1, 1, and then whatever z is here. What's 16 minus 1 minus 2? That's going to be at 13, I believe, right? Okay. And then where's this point located? This point is located at 2, 1. So that's 2, 1. So where's that one located? That one's located at 10, I believe. If I plug in 2 and 1 here, I get 16 minus 2, 4 minus 16 minus, right? 16 minus 2 is, no, sorry, 16 minus 4 is 12, minus 2 is 10, that's correct. Okay, and then this one here, okay, where's that one located? That one's located at 1, 2, okay, x1, y2. So this is 1, 2, and then that's going to be, I think, 7, right? Because we get 16 minus 1 minus 8. So that's 16 minus 9, which is 7. And then this one here, this one's at 2, 2. So 2, that's 4 minus 8, 16. So that's going to go all the way down to 4. Right? Okay. So how can we get the volume of this, approximate volume of this of this elliptic paraboloid? Well, what's the base area of each of these prisms? What's the base area of each of these 4 rectangular prisms? Well, aren't each of them a 1 by 1 prism? So wouldn't the volume be approximately 1 times 1 times 13 plus 1 times a height of 10 plus 1 times a height of, or sorry, 1 times 1 times a height of 7 plus 1 times a height of 4. And what are we basically doing? We're just basically adding up 13, 10, 7, and 4, which ends up being what, 34? And so the approximation is 34 cubic units. Okay, that's my approximate volume. Okay, does that make sense? Okay, so let me stop sharing. Okay, on this one, because now we don't have to analyze the graph so much on the next few, so we're good. Again, I wanted to make sure we had a solid understanding of this with a good graph before we moved on. So let's go back to my notes. Okay, so share screen. Let's go back to my notes. Okay, so example 2. Okay, so again, example 1 was just the 13 plus 4 plus blah, blah. Okay, just, you can put it down. Volume is approximately 1 by 1 by 13 plus 1 by 1 by 7 plus 1 by 1 by 10 plus 1 by 1 by 4, which comes out to be 34, right? Okay, but we really don't care so much, you know, about, you know, what's the approximate volume. Wouldn't it be really good to know what the actual volume is in that, right? So what are we going to do? Aren't we going to let m and n go to infinity, right? The number of rectangular prisms, wouldn't we want that to go to infinity? That's exactly what we're going to do. And then we use, you know, okay, so okay, we think of a double integral that way. Okay, the limit of this thing is going to go to infinity. Okay, so let's integrate this bad boy. Okay, let's see what happens when we do that. Okay. Okay, so we had the double integral, okay, of 0 to 2 in the y direction and 0 to 2 in the x direction. Okay, again, this is a rectangle. It's the same problem. Okay, of f of xy. Okay, and then we're going to do dy dx. And there's a reason why I do dy first. Okay, there's a reason why I do dy first. Okay, it's because I want to end up with a function of x at the end. Okay, of doing the integration. What we call this is, we call this iterated integration. Okay, we're integrating this guy first with respect to y, and then we integrate that function that we get, which is a function of x, with respect to x next. Okay, well, what was the function? Well, the function f of xy was equal to 16 minus x squared minus 2y squared, right? So let's see how we could get the actual volume by using an integral, which is a limit of Riemann sums. This limit of Riemann sums here, okay, to do this. So we're going to say, oh, okay, so this is 0 to 2 of 16 minus x squared minus 2y squared dy dx. Okay, put dy first. Okay, unless, you know, it doesn't work real well. Okay, you can reverse the order under special circumstances. Okay, but your default is going to want to be to do dy and then dx. Okay. Okay, think of it as we're undoing a partial derivative here. We're doing the anti-partial derivative of these, okay, of these functions here, okay, of this surface. Okay, so if I take this derivative, or I take this integral with respect to y, what am I going to get? Well, okay, aren't I going to get 16y minus x squared y minus 2/3 y cubed? And I'm going to evaluate that when y is between 0 and 2. Oh, okay. We're going to plug this in for y. Again, this is going to be integrated from 0 to 2 with respect to x. Okay, so let's plug in 2 and 0 for y. Now, if I plug in 0 for y, everything goes away. So I may not. I may not even put that in, but you can see that if I plug in 0 for y, everything goes away, right? It's gone. So let's just plug in the 2 for y. So 16 times 2 minus x squared times 2 minus 2/3 2 to the 3rd power. Okay, so this is going to be 32 minus 2x squared. Okay, minus, this is 8 times 2, which is 16. That's 16/3. Okay. Okay, I could plug in the 0 if I really wanted to, but just keep in mind this is going to be minus 0, minus 0, minus 0, which is 0. That whole thing is going to go to 0. Okay. So now what do we got? We've got 32 minus 16/3. Okay. So I could clean that up if I really wanted to. Okay, so I'm going to multiply 32 times 3. Okay, and that's going to be what, 96? All right. Okay, something like that. I don't know. Okay, so 32 times 3 is 96. So 96/3 minus 16/3 minus 2x squared. Okay, so let me just make sure I did that right. I'm good with the calculus. I'm bad with the arithmetic because it's just the way it is. Okay, it's just the way it is. Okay, I'm too calculator dependent, but that's okay. Okay, is 96. Okay, sounds good. And then minus 16, okay, is 80. Okay, so this is 80, 80/3. So we've got 80/3 minus 2x squared. Now let's go from 0 to 2 dx. Oh, well, this is just like a regular integration with respect to x now. Well, there you go. Okay, well, that's kind of cool. Okay, so let's integrate this with respect to x. So we've got 80/3 minus, this is now going to be 2/3 x to the 3rd. Okay, I'm sorry, this is 80/3 x. Okay, minus 2/3 x cubed. Evaluated from 0 to 2. Again, I don't really need to plug in the 0 because that's just 0. I'm going to plug in the 2 though. So this is going to give me 160/3 minus, this is 16/3. Okay, so what's 160 minus 16? Okay, what is that? 144? Okay, and what's 140? Again, I'm really bad on the, so 160 minus 16 is 144. Divide that by 3, and I get 48. Okay, so this is 144/3, which is 48 units cubed. So the actual volume here is equal to 48 cubic units under this. Okay, we kind of had this dealio here, this rectangular unit, right? And we had this thing coming down like so. I don't know if I can draw it real well, but right. And then we had our various guys come. Maybe I'll just draw it more like this. Get rid of that one. Okay, but you get the idea. Okay, I got my 4 points, blah, blah, blah. Okay, and the actual volume, okay, under this thing, okay, the actual volume under these 4 points, okay, the actual volume, total volume in that region, okay, is actually 48 cubic units, which is a far cry from the 34 that we got before. So the estimate was 34, okay, but the actual was 48. Make sense? Okay. do example 3 here. Did I make that example 2? Yes, I did. Okay, good. Let's do example 3. Okay, so we want to evaluate, okay, 0 to 2 and 1 to 2 of x minus 3y squared, okay, dy dx. No, not always. No, you do not. You can flip the order of integration. I'm gonna do that right now for you, Ashley, okay? I'm gonna show you, I'll do the next one both ways. Okay, I'll do it dy dx and I'll do it dx dy, but you have to make sure that you flip the limits of integration. Okay, the limits go to the variable, I can't think of the freaking word that I'm looking for. The respective variable, that's what I was looking for, respective. Okay, the respective variable goes to a certain limit and you got to keep those together. Okay, so if the original looks like this, evaluate this with respect to dy dx. Okay. Okay, I'll put an and here. Then what would happen if I flipped the order of integration? Well, it would go 1 to 2 and 0 to 2, but then I'd have x minus 3y squared from dx dy. Okay, and I'll do this both ways this time to just show you that you will come out with the same answer. But again, you got to keep the x's together and you got to keep the y's together. Okay, with their respective limits. Okay. Good question. Great question, Ashley. Thank you. It's a pleasure to have you in the class, by the way. Just wanted to let you know that. Okay. So A. Okay, 0 to 2, 1 to 2 of x minus 3y squared. Okay, and this was dy dx. Now, for most of the applications that we do, we're going to want to do dy dx first, and I'll explain that later. But you can flip them; it doesn't matter. Okay, and sometimes, say that we have something that looks like this. Okay, that I may want to do a dy dx on, or a dy dx. But if I have something that looks like this, I may actually want to flip the order of integration. It may make it easier. Okay, it all depends on the function or the surface that I'm given. Okay, so this is a cylinder right here, and this is a cylinder, but one's flipped on its side, right? Okay, it all depends on what's going to make it a function and what's not going to make it a function. I would have to, am I going to have to split this into two separate functions if I integrate the other way, or can I do it all as one function? It depends on the scenario, okay? But your default is going to be dy dx, okay? So you want to try dy dx first. If you run into problems, then switch it up to dx dy. Okay. Okay, so 0 to 2, 1 to 2. Okay, so we want to do with respect to y first. So this is going to be xy minus 3 over 3y cubed, evaluated from 1 to 2. Okay, so I'm going to go 2x minus, this is just y cubed, minus 2 cubed. Okay, minus 1x minus 1 cubed. Okay, right. Okay, so this is 2x minus 8 minus x minus 1. Okay. And then this is going to be distribute, that's negative x plus 1. Okay, plus, so this is 2x minus x, which is x. Negative 8 plus 1 is 7. So this is x minus 7. So now what do I want to do? Well, what did we integrate on? We integrated on 1, right?
Integrate dx.
Yeah, thank you, Jose. We want to integrate with respect to x. And what are my limits for x?
0 to 2.
Yeah, thank you. Very good. 0 to 2. Okay. Dx. Okay, so 0 to 2. Okay, we're going to integrate this guy. So this is going to become x squared over 2 minus 7x from 0 to 2. Okay. Okay, and so plugging in the 2, I want 2 squared over 2 minus 7 times 2. Okay, so 2 squared, this is 4. Divided by 2, which is 2, minus 14. So we get negative 12. So y is negative 12. That's going dy dx. Okay, so now let's do it the opposite way. Let's do dx dy. Okay, so this would be 1 to 2 and 0 to 2, right? And then x minus 3y squared. And so this is now dx dy. Let's see if we come out with the same result. Okay. Different order of integration. So we're going to get different values for our functions, but when we plug in the values, hopefully everything will work out the same. Okay, so I'm going to integrate with respect to x first. This is x squared over 2 minus 3xy squared. Okay, from 0 to 2. Okay. So this becomes 2 squared over 2 minus 3 times 2y squared. So this becomes 2 minus 6y squared. Now we integrated with respect to x. Now we want to integrate with respect to y. So this is 1 to 2 dy. So this is going to be 2y minus 6/3 y cubed, evaluated from 1 to 2. So we're going to plug in 2 here. 2 times 2 minus 2 times 2 cubed minus, here we actually do have to plug in everything, minus 2 times 1 minus 2 times 1 cubed. Okay, so here I'm going to get 4 minus, what is it, 16? So I got 4 2's there, so 16 minus 2 minus 2. Well, that's kind of cool. Okay, this goes to 0. And this is just negative 12. And lo and behold, doing dx dy also works. Check. Okay. Pretty snazzy. Who says that? Who says snazzy? Some old people. I think my grandparents used to say that. Turning into my grandfather. That's not good. However, I did see my granddaughter this afternoon. Or no. You don't have to do that. Okay. It just shows. I was just saying that the order. You just want the answer. Okay, the numerical answer. And if you're finding volume, then you just put units cubed. Okay, but in this case, we're not finding volume, we're just finding the numerical value. Okay, I was just telling you that for, doing it both ways here, dy dx, okay, or dx dy. Okay. Okay, or dx dy, either way will give you the same result. Okay, and it should if your function is a polynomial, it's really easy to show that it's going to work, or one of these quadric surfaces, right? Think of it as like a polynomial surface. Okay, these quadric surfaces, it's really easy to show that you can go integrate either direction. When we get into other functions that are a little harder, one way may be better over the other. Okay. You can do it, but one may be faster or more efficient or incur less errors. Or you may be able to do just one integral instead of 2 or 3. Okay. Okay, so let's see what else we got here. What do we got? Oh, we can separate them. That's kind of cool. We can do, they are separable if one of the products involves X and one of the problems involves Y, and there's no overlap. Then we can actually separate them. So if f of xy is equal to g of x times h of y, okay, then the integral over r, okay, of f of xy is equal to the integral from a to b of g of x dx times the integral from, okay, c to d of h of y dy. Okay, just saying, look, if one of your products involves only x and one of your products involves only y, then you can just integrate them separately. One with respect to x, one with respect to y, and then multiply them together. Okay, so let's do an example of this. Okay. Example 4, I believe. Okay, if the region that you're integrating over, the rectangular region, is 0 to pi over 2, okay, by, this x means by, okay, it's a rectangular region, by okay, 0 to pi over 2, so it's actually a square region, okay, and f of xy is equal to the sine of x times the cosine of y, integrate okay, over the region R of f of xy, dA. Okay, dA is just the area that you're integrating over. Okay. Okay, so let's set this up. So the area, how would I get my limits of integration here? And does it really matter which is x and which is y? Well, it doesn't, because this is a square region. And since the region for x and the region for y would be the exact same dimensions, we can do it either way. It really doesn't matter. But I'm going to do it, I'm going to say that I'm going to put it 0 to pi over 2, and then 0 to pi over 2, and then I'm going to say sine x cosine y, okay, and then I could do, let's do dx dy, okay, doesn't matter, I mean, it didn't matter if the 0 to pi over 2 went with the x or the 0 to pi over 2 went with the y, because they're the same, they're identical, okay, it doesn't matter in this case. If it did, they would have to tell us which one is the x and which one is the y, but they didn't tell us that because we didn't need it. It's a square region. We don't need that information. Okay, so we can do the problem without it. Okay, it's just saying, hey, you've got a square region here, 0 to pi over 2, 0 to pi over 2, and well, which one do you want to designate as x and which one do you want to designate as y? Well, it's the same thing. Okay. Now, because this is a product of two functions, one involving only x and one involving only y, I can separate these out. I can say, oh, well, this is equal to the integral from 0 to pi over 2 of the sine of x dx times the integral of 0 to pi over 2 cosine y dy. It's separable. Okay, I can separate them. Okay, so let's do the first one. Let's integrate this guy. Well, the integral of sine is negative cosine. So this is negative cosine x from 0 to pi over 2. The integral of cosine is sine, so times the sine of y from 0 to pi over 2. Okay, so plugging in the negative cosine of pi over 2, well, negative cosine of pi over 2 minus negative cosine of 0, okay, all of that times the sine of pi over 2 minus the sine of 0. Okay, well, the cosine of pi over 2, that's 0. Okay, so this is negative 0. Minus a minus is a plus. Cosine of 0 is 1. So this whole thing just goes to 1. Times sine of pi over 2, which is 1, minus 0. Sine of 0 is 0. So this just goes to 1. So it becomes 1 times 1, which is 1. So there you go. Nice. Okay. So I'll do another one here. We have number 5. Okay, if R is equal to 1 by 2 times, or sorry, is 1 by 2 by 0 pi. Now these are different. So which is which? Which do you think is X and which do you think is Y? Well, let's just say that, yeah, let's just do sequential order, right? Alphabetical order. I'm going to assume, if I'm not told, I'm going to assume that the first one is X and the second one is Y. Okay? Make sense? Okay, so I know there's a lot of assumption that's being done here, but if you're not told, just go with the first one as X and the second one as Y. Okay, go alphabetical order. Okay, so here's our area that we're integrating over, okay, and integrating our volume over, and we're going to say that f of xy is equal to y sine of xy. Okay, y sine of, sorry, x times y, no, x, y sine of xy. That's our function. And so we want to integrate this. Okay, so we're going to say that our domain, which is our rectangular region, okay, or R in this case, right? R is our rectangular region, okay, such that we have X and Y, such that X goes from 1 to 2, and Y goes from 0 to pi. Okay, so you can let this be D equals R. You can call it R for rectangular region, or you can call it D. D is the more generic. When I move into in a second doing these double integrals over general regions, then we're just going to call it D. But if you see an R, it's actually a rectangular region. Okay, which, you know, sometimes makes things nicer. Okay, so let's integrate, shall we? Okay. So what do we want to do first? Well, let's do our default. Let's do our default first. Let's try dy dx. Okay, is that going to be easiest? I don't know. We're gonna see. Let's see for a second. What's easier here? Is it easier to do dy dx, or is it easier to do dx dy? Because one of these is going to be easier. Okay.
Would it be dx dy? Or
yeah, why do you say?
well, just because I see that it's y times sine xy, like there's more y's, and since it's like a product, I guess, like y times the sine, it just seems like you do it with respect to y.
Yeah, if there's a product, what do we call the operation that we'd have to do?
For integrating it?
Yeah.
Integration by parts?
Exactly. Exactly. If we do dy dx, can you guys see what gosh, I forget how to pronounce your name. I apologize. Ismin. I think I got it.
Eastman.
Eastman.
Eastman, yeah.
Eastman. Okay. Eastman. Okay. Does everybody understand what she was saying? Was that if we do dy dx, we have two functions here involving y, which means that we would end up having to do integration by parts, okay, instead of eliminating a variable. If we do, so this requires integration by parts, which is not fun. We could do it. It would be fine. I could do it integration by parts if you really wanted me to, but let's not do that. Yeah, let's do x first. Okay, yeah, let's do x first, because then we can treat the y as a constant, right? This y outside gets treated as a constant if I do x first. Okay, does that make sense, Erica? Okay, so we have y sine of xy, and we're going to do dx dy, because this, in this case, it follows that it's just easier to integrate. Okay, so which one was the x? The x goes from 1 to 2, and which one was the y? The y goes from 0 to pi. Okay. So now when I integrate this, what am I going to get? I'm going to get negative y cosine of xy. If I were to integrate the inside, if I were to kind of do integration by parts, or not integration by parts, if I do a u sub on this, maybe I'll do that. Maybe I'll just do the u sub so I don't confuse anybody. He's like, well, how did you get the integration factor? I'm like, well, I did the u sub in my head. I'm not going to do the u sub in my head, okay, even though I can. Okay, so let's do the u sub here. U is equal to xy dx. Okay, so what's du? Well, du is going to be with respect to x, right? We're integrating with respect to x. Du is going to be y. Or sorry, u is equal to xy. Du is equal to y dx, and so du over y is equal to dx. Okay, so that would mean that I would divide by a y. Oh, isn't that convenient? Okay, that I end up dividing by a y. Oh, okay. So if I said, this goes from, okay, and I would have to change my limits of integration as well if I did this u sub. So if I plug in 1 for x, I would get y. And if I plug in 2 for x, I would get 2y. Okay, so that would be, and then it would be y times the sine of u times du over y. But notice that y cancels. Oh, that's kind of cool. So now it's just the integration of sine u, which we know is negative cosine u, evaluated from y to 2y. Okay. So this is negative cosine of 2y minus negative cosine of y. Okay. So this is negative cosine 2y plus cosine y. And I'm going to integrate that now with respect to 0 to pi dy. Okay. Nice. Okay, again, I could have done the u sub in my head if I really wanted to. I would just do, oops. How do I unpause? Stop. Resume my sharing. There we go. Sorry, I could have done it in my head if I really wanted to. If you wanted to kind of do this u sub in your, or do the integration in your head, you could say, hey, I'm treating y as a constant. So I would get y times, this would be negative cosine of xy. And then you'd say, well, what's the derivative of xy? It's y. Divide by that y. And you would get the same thing. And then you wouldn't have to change your limits of integration this way. You would just go from 1 to 2. But you're going to end up with the exact same thing. There's just two ways to do the same thing. Okay, but it just depends on how adept you are at your integration skills. Okay. Okay, so cosine 2y plus cosine y dy. So now let's integrate this guy. Okay, so this is a U sub. Again, you could do the U sub in your head if you really wanted to. Just means that I'm going to have to end up dividing by 2. Okay, but I'm going to make this negative sine of 2y over 2. Okay, plus this is going to be sine of y. Integrate from 0 to pi. Okay, so plug in pi. This is negative sine of 2 pi over 2 plus the sine of pi. Okay, minus negative sine of 0. Oops, negative sine of 0 over 2 plus the sine of 0. Okay, it's actually 2 times 0, but it's just 0. Okay, the sine of 0 is 0. That goes to 0. That goes to 0. The sine of 2 pi is also 0. So we just get the sine of pi. Okay, what's the sine of pi? Well, the sine of pi is also 0. Everything goes to 0. Okay. One last thing on this that you should know is that the average value, okay, of f of x, if you want to find the average value, it would be 1 over, okay, the area of R. Okay, this is the area of R. Okay, 1 over the area of R. Okay, times the integral of R, double integral of R of f of x, y, dA. Let me check that for a second.
That was easy.
Oh, no, it wasn't. This is Calc 3, bro. It's not easy. Just quit your yapping. Knock it off. Okay. If it was easy, everybody would be an engineer, right? Everybody would be doing this stuff. Okay. It's not easy. That kind of pisses me off sometimes when people come up to me and they're like, well, what do you do for a living? Like, right, that's what everybody asks, right? And then they're like, I'm like, well, I usually my go-to is I'm a teacher, until they start prying more. Because I don't want to tell people what I do for a living, because sometimes it puts them off, like they don't know how to relate to me after they find out what I do, right? They're like, okay, you're a freak of nature, and they treat me differently. So I usually say, oh, I'm a teacher. And they're like, oh, okay, I know what that is. And then I get the occasional people that pry a little bit further, and they're like, well, what do you teach? I'm like, I teach math. I'm like, oh, okay, so you're a math teacher. I'm like, yeah, exactly. And then I get the occasional person that pries even further, and they're like, well, what level of math do you teach? I'm like, well, I teach college. And then they're like, oh, you teach college. And then I get the occasional person who pries even further and says, okay, what specifically do you teach in college? And I say, I teach calculus 3. And I teach statistics. Those are the 2 things that I teach. And at this point, I've either made an incredible friend because they've pried so much, or I've made an enemy for life because they don't know where to go from there. But then I will get the occasional jerk who says to me, oh, you must have an incredible gift. And that pisses me off. Does anybody know why that pisses me off? When people say, oh, you have an incredible gift.
Because it's more like hard work than it is just natural talent.
Exactly. Exactly. They just discounted the tens of thousands of hours that I put into my craft to get to the point where I'm at. See, I'm no smarter than you guys. I'm just a lot harder of a worker. So, you know, I just keep that in mind, okay? So anyway, so
That was easy.
you're right. I guess it was easy. That's my easy button, okay? Okay, so I want to check, I want to make sure that I gave you the correct formula here. 1 second. Because in my notes, it's written wrong, and I want to make sure that it's written correctly here. Okay. Yes, that's correct. Okay, good. I was right. Okay, so this is the area of R. Okay, this is the area of R. Okay, let's move on to 15.2, where we get into the real fun stuff. Okay, so the real fun stuff, which is integrating over general areas, not rectangles. Okay, we're going to integrate over general areas here. Okay, so we're going to have a function of one of the variables as our limits of integration. So it looks like this. It just says, hey, we're integrating over D of f of xy. This is 15.2, by the way. Double integrals over general areas. Okay, double integrals over general areas. Okay, so f of xy dA is equal to a to b of g1x g2x. Okay, and now we see that, oh, okay, this was a function of x, right? This was a function of x, that were my limits. So I might want to think of this as y1, y2. Okay, this is y2 and this is y1, right? Okay, this is where the y's are going from. The y is going from y1 to y2, which means that I would want to integrate with respect to y first and then with respect to x second. Okay, so where D, this is why I wanted to set it up that we integrate with respect to y first, because if we have our functions designated in terms of y equals, then I can say, oh, y equals, 2x, so it's going to go from 2x to square root of x or something like that. We're going to have the x variable in our limits. The x variables are going to be in our limits if we integrate with respect to y first. We'd have to switch it around if we integrated with respect to x first. Now, with respect to rectangular domains, it really doesn't matter so much. Okay, you can go back and forth. But when we're talking about functions and designating things as functions, yeah, you got to be very careful about switching your order of integration, because now you have to switch functions and you have to find inverses of functions. It really gets kind of like not too fun. Okay, so you got to make sure which order are we doing it so that we can get our domain correctly. Okay, where D, okay, is going to be, okay, xy such that, okay, x is going to go from, okay, A to B, but y is going to go from G of G1x1, or sorry, G sub 1x, G sub 2x. Okay, so y is a function of x. Okay, the boundary is G1x, G2x. Okay, for the y values. Okay, let's see how this works in real life here. Okay, so number one, evaluate okay, over D, okay, of, well, that's not, why does it want to do my into shape? I don't want into shape. Take that darn thing off. Into shape, there we go. Okay, D, okay, so D is x plus 2y dA, where D is the region, okay, bounded by the parabolas y equals 2x squared and y, okay, so we want to evaluate this double integral, okay, where it's the region bounded by these two parabolas. Okay, so we've got some issues here. We got to figure out, okay, what do the y's go from and what do the x's go from? So what do you want to work on first? Well, maybe we'll work on the y's first, okay? So, and then we'll work on the x's. Okay, so if I were to graph these parabolas, right? What do these parabolas look like? Well, I would get one that looks like this. Okay, this is y equals 2x squared. Okay, and I'm going to change colors. And I would get one that looks like this. Not like that. No, oh my gosh. Not like that either. Okay, let's go to 1, and I'm going to go out from here. Okay. We get this guy here, right? Okay, does that make sense? Okay. Bad drawing. Okay, 1 is going to go through 0, 0, and it's going to be thinner. Okay, 1's going to go through 1, and it's going to be less thin. I don't want to say fatter, because that's you know, you always want to be politically correct when you're talking about your parabolas, because then they'll just they're going to get angry with you. So we'll say it's less thin or wider. Is wider okay? I'm going to say wider. Okay, so okay, guys, can I give you a heads up here? Okay, guys. Okay, whenever you're asked a certain question, do not answer, okay, it's not the dress. Okay, so don't answer the specific question as it's not the dress. So when somebody says, does this dress make me look a certain way, and you answer, it's not the dress, that's a bad move. Okay, and I'm speaking, unfortunately, from experience. Okay, that was almost a filing of the courts. Okay, so I'm just giving you a heads up. Okay, don't make that mistake. Okay, that's a rookie move. Don't do that. Okay, anyway, back to the calculus. Sorry, I digress. Okay, so where are the y's going from? Which function is on bottom here? What's the bottom function? If I want to do my limits of integration, which function is going to have lower y values? Well, it's this guy, right? Isn't it the 2x squared? Okay, isn't it the 2x squared there? Okay, and then which one is on top? Which one's going to have the higher y values? It's in this region, in the region that I'm looking at in the overlap, the region bounded by these two, in that region, Okay, the one that's on the bottom is the 2x squared. So I'm going to say, oh, okay, this is going to go get my limits of integration here. Limits of integration. Maybe I'll color code this. Okay, no, I won't. Okay, so limits of integration of, okay, between these two, okay, of the intersection, okay, of this, right? Okay, this is going to go from 2x squared to 1 plus x squared, right? And that's going to be dy dx. Why dy? Because my limits of integration are with respect to y. Okay, think of this as y equals and y equals, right? From y equals 2x squared to y equals 1 plus x squared. Okay, so the one that's on the top, okay, is 1 plus x squared, and the one that's on the bottom is 2x squared. Okay, so so now what do the x values go from? Now the x values are going to have to be numerical values. They can't be functions. You can't say, well, the x values are functions of x. Well, yeah, they are a function of x. Well, okay, then that's a one-dimensional function. So if it's a one-dimensional function, then this is gonna, okay, well, how do we find out where the x values go from? Well, we have to set these functions equal to each other and solve. Right? So we're going to set them equal to each other. So we're going to say, oh, okay, 2x squared is equal to 1 plus x squared. Okay. So subtract x squared. I get x squared equals 1. And then x is equal to plus or minus 1. Oh, okay. So this was at negative 1. Now it's at positive 1. So the limits of integration go from negative 1 to positive 1. Okay. And then what's the function that I want to integrate over? It's x plus 2y. That's the function. This is just the domain. Okay, this is the domain. Okay, that's in the xy direction. That's in the xy plane. But our function is a three-dimensional function, and we want to we're actually finding the volume under this function. Okay, we're finding the volume under this function. So we're going to go x plus 2y is our surface. So the volume under this surface, we're going to now have to integrate. Oh. So we're going to integrate this with respect to y first. Okay, so this is xy plus y squared integrated from 2x squared to 1 plus x squared. So I'm going to plug this in, okay, for y. Okay, so we're going to get x times 1 plus x squared plus 1 plus x squared squared, okay, minus x times 2x squared, okay, minus, plus, sorry, 2x squared squared. Okay. Nice. Okay, so let's kind of try to clean this thing up if we can. Okay, so this is going to be x plus x cubed. If I square this out, I'm going to get 1 plus 2x squared plus x to the 4th. This is going to be minus, what is this? 2x to the 3rd, and then minus 4x to the 4th. Right? Okay, so let's clean this up. What can I clean up here? So I've got an x to the 3rd and a negative 2x to the 3rd. That's going to be a minus x to the 3rd. So I've got an x plus 1 plus 2x squared plus x to the 4th minus x to the 3rd. And oh, I have an x to the 4th and a minus 4x to the 3rd. Or minus 4x to the 4th. So it's a minus 3. Minus 3x to the 4th. Okay. Oh, sorry. Should be like this. Minus x to the 3rd minus 3x to the 4th. Okay. So now what do I want to do? Well, now everything's in terms of x. And I want to integrate from -1 to 1. Okay, and so now I want to do with respect to x. Okay, so, oh, how did I get the x plus 2y? Yeah, that was in the original. That's the surface, right? That's the surface. So if you kind of think about it this way, and remember, everything we're doing in multivariable calculus is three-dimensional, right? So we're saying, hey, we have this x and y, right? We have these parabolas on the xy plane, okay? And this guy here is going to be under a certain surface. Right? And we want to find the volume. Oh, that's bad. We want to find the volume of this like crescent shape. I want to find the volume of that crescent shape under that surface. So hopefully that helps. That's a good drawing, actually. I'm kind of impressed with myself on that one. Okay. Does that make sense?
Yeah, it does. Thank you.
Okay, good. Okay, so yeah, this is a function of xy, okay, which is our original, which was our original x plus 2y, right? Actually, it doesn't even look like that. It's not even a curved surface because it would just be a plane, right? Because it's just x plus 2y is just a plane. So this would be a plane slicing through three-dimensional space. Okay, and so I could have probably drawn it even nicer or more accurate, but I guess I'm not as impressed with myself as I thought I was. That's usually the case. Okay. It's good. It's good to have somebody else in your life that reminds you of that too. Okay. It's very humbling. Okay, x plus 2y. Okay, so now let's integrate this bad boy here. I'm sure you could integrate this easily. Everybody knows how to do this, so I'm not going to spend much time on this. Okay, so this is x squared over 2 plus x plus 2 thirds x cubed minus 1/4 x to the 4th minus 3/5 x to the 5th. From -1 to 1, you plug in 1, you plug in -1, and you're going to come out with 32 over 15. Again, I'm not going to spend any time on the arithmetic there. You can convince yourself of that if you really want to. Okay. Okay, let's see what I want to focus on at this point. I don't want to do that one. Waste my time. All right, I'll come back to that. I'm going to think about that for a second. Let's do one that's a little bit more interesting. Okay. Okay, so what are we on number 2? Number 2. Okay, find the volume of the tetrahedron bounded by the planes x plus 2y plus z equals 2, comma, x equals 2y, x equals 0, and z equals 0. Okay, so yeah, it's bounded by these planes. Okay. Okay, so the first thing I want to do is I want to look at this guy here. Okay, and I want to say, well, that's a plane. Okay, and that's going to be I want to set this equal to z. I want to solve for z. So that's a function of x and y. So if I solve this guy for z, x plus 2y plus z equals 2. I'm going to toss these guys to the other side. I'm going to get z is equal to 2 minus x minus 2y. Okay, and that's going to be my function of x, y. Okay, so this is my plane. This is the surface that I'm going to kind of integrate under. Okay, this plane here. Okay, so I have the line x equals 2y, x equals 0, and z equals 0. Well, what does that mean? Okay, let's look at what that looks like. Okay, so we have a plane. Okay, let's just when we could find out a few points on this plane as well if we really wanted to, but let's see. Let's see what happens when is z 0? Okay, when z is 0, let's z equals 0, then x plus 2y equals 2. And so if I then let's let x be 0, let x be 0. Then y equals 1. So I know that there's a point 0, 0, 1, 0. Okay, which is on this region. Okay. Okay, you can think of it as a vertex, a vertice on my tetrahedron. Okay, so 0, 1, 0. Where's that going to be located? It's going to be located here. Okay, 0, 1, 0. Okay, if we let y be 0, then x is equal to 2. So this is going to be 2, 0, 0. So that's another point on my tetrahedron. Where's that going to be? Well, it's going to be here. Okay. Okay. And then what happens if x and y are both 0? What happens when x and y are both 0? Z is equal to 2, right? So let x and y both be 0. Then we get z equals 2. So this is 0, 0, 2, which is another point on my tetrahedron. Okay, so we've got this guy like so. Okay. Okay, with one caveat though. We also have a plane here that's slicing this thing. Okay, we have this disclaimer here that it's not this whole region that's under this, because why? Because we have this other plane, x equals 2y, that's going to slice this thing vertically. It's going to get a vertical slice here. Okay, and so let's get a couple of points on this line in the xy plane. So if if x is 0, then y is 0. So let's look at this thing here. Let's look at x equals 2y. I'm going to go to red here. X equals 2y. And let's just do a t-chart. If x is 0, then y is 0. If y is 1, then x is 2, right? Okay. So if y is 1, x is 2. So I have a couple points here. I have a point 0, 0. Okay. I have the point 0, 0. And then I have, okay, okay, and then I have, let me think about this for a second. And then I have the point, okay, the point 2, 1, right? So out 2 on the x, okay, out 2 on the x, and then 2 on the y, right? Okay, so we are actually going out this direction. Okay. However, we would go out that direction forever. Where do these two intersect? Where does that boundary of that plane intersect with this thing? Well, okay, this thing, okay, let's think about what this line is. Okay, this one would be that boundary there. Let me put it in black. Okay, that's the slice that's being made by just this plane. But again, we're going to have to slice this up vertically. Okay, we're going to get a vertical slice here. Okay. You're going to get this plane that's going to slice this up vertically. Okay, that was really bad. I'm going to get rid of that. Why can I not undo without having to? There should be like Control Z or something. Undo. What the heck? Undo. Okay. Got to be a shortcut. Here, what are the freaking shortcuts? Help. Help. Okay. Undo shortcut. Right here? I don't want to write there. I want to write here. Undo short. Undo an action, Command plus Z. Command Z. Okay. Command Z. Okay. Control Z. Nice. There we go. Control Z. Okay. So I'm just going to do it like that for now. Okay. And then I'm going to say, well, we're going to actually slice down to this point here. Problem is, I need to know which side of this I'm on. Which side of the cut am I going to be on here? Okay, and where is this point located? Okay, well, okay, we have this line here. If we go to an XY plane, it'll be a lot easier to see. We have the XY plane here, right? And we have 1, 2, and 1, right? And so we have this out like this, and then we have this right here. Okay, so where are those two intersecting? Right, so where are those two intersecting? Well, this is y equals, I would say 1/2 x, right? So the slope here is 1/2 x, right? Okay, whereas the other way, no, this is, it was, yeah, y equals 1/2 x. Exactly what it is. Okay, so that's the red one here. Y equals 1/2 x. Okay, and then what's the other one here? Well, the other one has a slope of negative. That has a negative 1/2. Oh, okay. So this is y equals negative 1/2 x. Okay. So okay. So when are these two equal? Is that right? Because this is a 1/2. This is 1/2. And I just want to know, well, where, I mean, we can easily see that that those two are going to intersect at 1/1/2, because it's a rectangle. But why is this not working? Oh, this is negative 1/2 x plus 1. That's why. That's what it is. Okay, negative 1/2 x plus 1. Okay, so because the y-intercept is at 1. So if I set these two equal to each other, okay, negative 1/2 x plus 1 equals 1/2 x. If I add the 1/2 x, I get x equals 1. And if I plug in 1, I get y equals 1/2. So this is going to be the intersection. Whoa, what the heck? Okay, the intersection of this point here, point that I'm going to put in purple. Okay, this point here is going to be at x equals 1, y equals 1/2, and z equals 0. Okay. So we know that this is slicing this up. I just want to know, is it going to be on the left side that the region is going to be sliced, or is it going to be the right side that the region is sliced? And that's going to be the other planes that we're going to look at here. Okay. So what are the other planes? Well, it's saying that it's being bounded. Okay, it's being bounded by the plane. The plane z equals 0. So that's the floor. So we have a boundary on the floor here of z equals 0. But it's also bounded by x equals 0. Okay, well, where is x equals 0? Well, isn't that the zy plane? Isn't x equals 0 this zy plane over here? So which part of this is going to be bounded? Well, it's going to be bounded such that we don't have this part anymore. Okay, I'm going to just erase this part here. This is gone. Okay, that part's gone, and all that's left is this tetrahedron. Okay, it's kind of hard to see that it's a tetrahedron from the way that I drew it, but just trust me, it is. You're like, what's the tetrahedron? Well, the tetrahedron is this, okay, and then it goes down to this point here. Okay, it's really hard to draw given the angle that I drew it at, but then it goes like this as well. Okay, and that's the tetrahedron that we're looking at. Oh, okay. So that's good. Okay, so what's the domain of this? That's what I really want to know. I want to know what's the domain. Well, this point again is at 0, 1, 0. Keep that in mind. That point right here is at 0, 1, 0, and this point up here is at 0, 0, 2. Okay. So again, what's the domain of this thing? Okay, so let's look at what is just in the xy plane on this thing here. We know that it has a y-intercept of 1. Oh, okay. So if I go back to this guy here, okay, I know that the y-intercept is included, but I also know that this line, x equals 2y, is a boundary. Oh, okay, so we can get rid of this, and we can get rid of this. And so what is the domain here? Well, it's just this region. It's this triangular region here. Okay. Okay. So how would I integrate over that triangular region? I'm going to blow this up. Okay, I'm going to zoom in on this triangular region. How would I integrate over that triangular region? Okay, if I were to make this an integration, right? It would be like, oh, okay, how would I integrate over this triangular region? Okay, I would have my top function and my bottom function, right? Top function, bottom function. Okay, so this was out at 1. Okay, this was, let's do a 1 by 1 square. This was, okay, this is going to be 1/2. I'm going to be right here. We're going to be here. And then we're going to be here. And I just want to know, oh, okay, so how would I get my limits of integration? dy dx. My limits of integration here. Well, what's my top function? My top function is y equals negative 1/2 x plus 1. What's my bottom function? My bottom function is y equals 1/2 x. Oh, okay. So the y values are going to go from, and I'm going to do a slice here. I'm going to do a vertical slice. Okay, and I'm going to say, hey, I'm going to integrate from the top to the bottom, and then I'm going to have all these slices, and I'm going to sum up all those slices. I'm going to sum up an infinite number of slices here. And so I put a vertical slice to show, oh, okay, yeah, I'm integrating with respect to y first, and then with respect to x. I'm going to find out what's the distance between that slice, what's the length of that slice, and then I'm going to sum up all the slices. Okay. So what's the bottom function? The bottom function is 1/2 x. What's the top function? It's negative 1/2 x plus 1. And where do the x values go from? Well, they go from 0 to 1. Oh, okay, that's kind of cool. Okay, and then what's the function that we're integrating under to get our volume? Well, that was this top surface function here in purple, which is this guy. It's that guy right there. Okay, this is my purple function. Okay, this front surface here, okay, is that slice that I'm integrating under, okay, is this function here. That guy there. Okay, so let's put all the pieces together and we'll integrate. 0 to 1, 1/2 x to negative 1/2 x plus 1 of 2 minus x minus 2y dy dx. Okay, so integrate with respect to y first. So this is 2y minus xy minus y squared from 1/2 x to negative 1/2 x plus 1. Okay, let's plug this in. Okay, 2 times negative 1/2 x plus 1 minus x times negative 1/2 x plus 1 minus 1/2 x plus 1 squared minus, okay, 2 times 1/2 x minus x times 1/2 x minus 1/2 x squared. Okay, distribute the 2. This is negative x plus 2. Okay, distribute the negative x. This is going to be positive 1/2 x squared minus x. Okay, square this out. This is going to be minus 1/4 x squared plus x. And how did I get that? I doubled 2 times 1/2 x times 1. Okay, because that's how you square a binomial, right? You
Oh
multiply.
wait, I think it's negative 1/2 x plus 1 squared.
Is it negative 1/2 x?
I think so, because then it would be
Oh, yes,
1
yes,
plus
yes,
x
thank
squared
you.
minus x.
Yes, yes, thank you. Right. Yes, 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 perfect. Thank you. So this is going to be still positive. So this is minus x. Thank you. Okay. And then this is plus 1. Yep. This is going to be minus x minus 1/2 x squared. And then this is minus 1/4 x squared. Minus 1/4 x squared. Okay, let's do some distributing and combining. So this is negative x plus 2. Okay, so negative x and well, I'm just going to write it like this. Well, I'm just going to write it like this. Negative x plus 2 plus 1/2 x squared minus x minus 1/4 x squared plus x minus 1 minus x plus 1/2 x squared. Okay, plus 1/4 x squared. Okay. So this 1/4 x squared gets canceled with this 1/4 x squared. Okay, this 1/2 x squared combines with this 1/2 x squared to become just x squared. Okay, we've got a negative x, a positive x, and a negative x. So that's going to be negative 2x. And then I've got a negative 1 and a positive 2, which is going to be minus 1. And we're going to integrate this whole thing now with respect to x from 0 to 1. Oh, okay, that's easy. So this is going to be x cubed over 3 minus x squared minus x from 0 to 1. This becomes 1/3 minus 1 minus 1. Or sorry, this should be plus 1. I'm sorry. Plus 1. And so those cancel, and I'm left with 1/3. Okay. Okay, I don't have time to do another example, so I'm going to stop here.